Okay, so good morning. So for the midterm 2, I have posted the solution to Canvas. So if you have any questions, feel free to discuss with me in the office hour. Yeah, I think one or two of the problems are a little bit tricky, like how to compute the CDF of a certain joint distribution. The integration sometimes is very tricky. So yeah, if you you can read the solution set first, and if you find any questions, so please discuss with me in the office hour today. So we'll continue the discussion last time. Well, we start to get into the higher dimension space. We are talking about n-dimensional random vectors. Now everything is pretty much the same, except that now every x represents a vector of random variables. So every coordinate is a single random variable. Okay. And also for y, for a vector of y, it is also a vector of random variables. And we can define the mean in a coordinate-wise sense, a very straightforward extension. And more importantly, we can define all these second-order statistics, the autocorrelation matrix, which is basically the expectation of x times x transpose. And this is the language of linear algebra. Okay, so we will use linear algebra to write all the formulas instead of listing all the coordinates one by one. Okay, this is very complicated. So try to use the linear algebra, the matrix vector multiplication notations to simplify your notation. And we can also define this autocovariance matrix, which measures the covariance between vector x and itself. And basically, if you look at the, for example, if you have two vectors A and B, right, you do A, B transpose. Now, this is essentially a matrix that gives you all the pairwise product between the coordinates of these two vectors. So you have A1, B1, A1, B2, and A1, BM. And then A2, B1, until AN, B1. Now, the way to understand this matrix is like, if I look at the ij's entry of this matrix, meaning the ith row, j's column, the ij's entry of this matrix, it is basically ai times bj. The ith row, the j's column. So here's ai times bj. So with this, we can understand this all these correlation, covariance, cross-covariance matrices in this way. Basically, if you look at ij's entry of this matrix, this correlation matrix, it is basically corresponds to the ij's entry of this Rx, this autocorrelation matrix. It is basically corresponds to the correlation between xi and xj. Where xi is the ith element of this random vector, right? The ith row. And xj comes from the j's element of this row vector. X transpose is a row vector. So it's ith row, j's column. So we get the correlation between xi and xj. So it's a collection of all pairwise correlations between xi and xj's in these coordinates. And similarly for this covariance, autocovariance matrix, Cx. Again, if you look at ij's entry, it is basically the ij's entry of this correlation matrix minus the ij's entry of this matrix. And you can check that it is essentially the correlation between xi and xj minus the product of their mean. Which by definition is the correlation, at least is the variance. Let me see, it's the covariance between xi and xj. So this autocovariance matrix simply collects all the pairwise covariances between these random variables in a matrix, in a big matrix. Now the cross covariance matrix is the same thing. So in this time is given by the ij's entry is given by the covariance between xi and yj, right? Because you have x and y. So it's it's the covariance of all the pairwise between all the pairwise random variables coming from the random vector x and the random vector y. So all the pairwise covariances. Now with this, we can have this all these properties of covariance matrices. So basically, if a random vector, if all these random variables are pairwise uncorrelated, then the autocovariance matrix is orthogonal, which can be seen from this expression. The ij's entry is simply the covariance between xi and xj. So only if I is not equal to j, right? If this entry is not on the diagonal line, if I is not equal to j, then xi and xj, these every two different random variables, they are pairwise uncorrelated. Right? Pairwise uncorrelated meaning that the covariance is zero. Right? This is from the single random variable result. So therefore, all the off-diagonal elements, x when I is not equal to j, all these entries are zero. The only special case are those entries who lie on the diagonal line. This happens when I and j are equal, right, on this diagonal line. And in that case, we're looking at covariance between xi and xi itself. That is essentially the variance of this random variable. Okay. So basically, this one is the variance of the x1. So we denote it as sigma 1 squared. And this is the variance of x2. And this is variance of the last random variable. So once we have this understanding, these properties are very easy to understand. Simply look at the pairwise statistics between these random variables. And the second one, if all these x and y's are pairwise uncorrelated, then the covariance matrix is zero, which can be seen from this one. The covariance matrix between x and y, these two vectors, is given by, so the ij's coordinate is given by the covariance between xi and yj. But now they are pairwise uncorrelated. So meaning that every such pair has zero covariance. So this is a zero matrix. And this, in particular, this auto covariance matrix, which is the covariance between random vector X with itself. This auto covariance matrix has some nice properties. So go back to here, that this is the definition of this auto covariance matrix. You see, it is a very special one that characterizes the covariance between X and itself. So this matrix has many nice properties. First of all, it's a symmetric matrix because it's the covariance between X and itself. So it is symmetric, which can be seen from this expression. If you take a transpose, does not change this matrix. So this is a symmetric matrix, and also it is positive semi-definite. So these are all linear algebra concepts. So okay, I will just follow the slides. Now we call a matrix positive semi-definite if for any vector A, such a quadratic expression is always non-negative. Okay. So CX is a square matrix, right? This n by n square matrix. Let's say X is X1 to Xn. It is, so first of all, by definition, it is symmetric because it's an autocorrelation matrix. To see this, the ij's entry of this matrix is the covariance between xi and xj. But the symmetric coordinate, which is the ji's entry, is the covariance between xj and xi. So these two, they are equivalent, right? Because xi and xj, changing the location does not, changing this order does not change the covariance between these two random variables. So it is symmetric. A positive semi-definite meaning that if I pick any vector, column vector A, and I do A transpose CX times A, right? This is a number because A transpose is a row vector, CX is a square matrix, A is a column vector. So with matrix multiplication, this is a number. Right? This number is always positive for any arbitrary vector A. If this holds, we call it positive semi-definite. The reason is that if we write out the full expression for this product, right? So CX by definition is the expectation of X minus the mean times the transpose of this vector. Right? This is the autocovariance matrix definition. Now we need to multiply this matrix by A transpose on the left-hand side and by A on the right-hand side. So this would become, well, this is A transpose, which is a row vector. Now X minus its mean is a column vector, because by default, X is a column vector. And here we have X minus the mean taking the transpose. So this is like the row vector. So this is X minus the mean. And this is X minus the mean to the transpose. And A, again, is a column vector. So by the previously, we know that this product will generate that autocovariance matrix, right? So column times row vector. So this will generate that square matrix. But now it has a very special structure. This matrix is actually generated by a product between a column vector and a row vector. So we can try to calculate this such an entire product by combining the first two and the last two. Right. The first two is a row vector times a column vector. So it's A transpose this vector, which gives us a number, a scalar, right? And the next one is the x minus mean to the transpose times this column vector A. Right. So this can be viewed as the transpose of the first one. Okay. Basically, if I denote the first product as Z, well, this Z is a number, right? Because it's a row vector times a column vector. Then the second product can be understood as Z transpose, right? Okay, so this is, to be more specific, this is the first product. This is the first product. We call this Z. So to get the second product, we look at Z transpose. Right, so this is Z to the transpose. But Z is a scalar, so the transpose itself is itself, it doesn't matter. But taking the transpose by matrix transpose rules, we know it equals to the second vector taking transpose times the first vector taking transpose. But the first vector is A transpose. So A transpose taking transpose is A. Right. So this gives us the second product. So this is actually Z transpose, but in this special case, Z is a scalar, so Z transpose equals to Z. So these two can be multiplied together directly. So we are looking at E expectation of Z to the power of 2, where Z is defined as such a random variable. And of course, because the square, this is guaranteed to be non-negative. Yeah, so this shows that for any arbitrary A, this product always takes a square form and is therefore always non-negative. So this shows this autocovariance matrix is positive semi-definite. It's a PSD matrix, a very important structure of this autocovariance matrix. And because of that, in linear algebra, we know that if a matrix is symmetric and positive semi-definite, okay, this is a very, very nice matrix. And we can do eigen decomposition. So we can introduce the eigenvalues and eigenvectors of this matrix. So all these are very standard tools from linear algebra. So this is like a review of all these technical concepts. So, okay, for any symmetric and the PSD matrix, we can define its eigenvalues and the eigenvectors. So basically, suppose a matrix M is symmetric and positive semi-definite. Symmetric and positive semi-definite. We can define the eigenvalues and eigenvectors by this equation. Well, if we can find a lambda, a scalar lambda and a vector v with unit norm, it's like a normalized vector. If we can find such a lambda and v that satisfies this equation, then we call such a v the eigenvector and lambda the eigenvalue associated with this matrix M, okay, with this symmetric and positive semi-definite matrix. You may find a lot of such vectors v and lambda. So we call each pair a pair of eigenvalue and eigenvectors. Right? The reason that this equation is so important is that such an eigenvector v can be understood as a basis of this matrix. So if you look at this matrix, basically, after applying this linear transformation M to this vector V, the resulting vector does not change the direction, right? The resulting vector is still pointing, is still aligned with this vector V. So therefore, this linear transformation M applied to such a vector V does not change the direction of this vector. So this means that this V is a very fundamental basis vector for such a linear transformation. Okay. So there are a lot of ways to find these eigenvalues and eigenvectors. I think if you take linear algebra, you should be able to, you should be very familiar with those. Basically, it reduces to solving such a linear equation. Okay, solving such a linear equation. So I will not go over these details because we will not solve these equations in this class. So we assume that you can apply this standard linear algebra techniques and get these lambda and v's. Okay, we will index them using subscript I. So it's lambda I, the i's eigenvalue associated with the vi, the i's eigenvector. And in particular, these eigenvectors, they are pairwise orthogonal. Okay. So first of all, if you pick any two eigenvectors, so okay, all these eigenvectors has unit norm, so they are a standard vector that has a unit norm, normalized norm, and they are orthogonal to each other, right? In this sense. So Vi transpose Vj, the dot product between Vi and Vj is 0. So we call them orthogonal. So basically they form a basis, right? Pairwise orthogonal and has a unit norm. And then what we can do is that once we have this lambda and v's, we can decompose the matrix, the original matrix M, using this lambda and v's in a very compact form. And this is how we do the decomposition. We first, so once you compute all these eigenvectors, right, we will stack them. We will stack all these column vectors into a big matrix. Okay, so we can define this V matrix, which is a concatenation of all these eigenvectors. So here we assume that you can find n eigenvectors. So it's n by n matrix. Yeah. You find all these eigenvectors, you put them in a row, you put all these column vectors in a row, right? That forms a matrix. And this matrix has very nice properties. First of all, it is a orthogonal matrix. So V transpose V actually equals to the identity matrix, diagonalized identity matrix. You can do this computation by yourself. So this V, if you look at this V is V1, V2, Vn stacking in a row, right? So this is kind of a little bit advanced linear algebra notation. So each V is a vector. Now we stack, it's a column vector. We stack them in a row. Okay. So this is actually a matrix, but we can write it in a row vector because now every V represents a column vector. So this is all these eigenvectors, right? This definition V. So following this notation, V transpose is basically the transpose of this vector. Now this looks like a row vector. So when you do the transpose, it will become a column vector. But then each coordinate inside should also take transpose. So in this case, V transpose can be written in such a column-wise form. Well, each coordinate is the transpose of the corresponding coordinate of the V. And this transpose cannot be ignored because originally this V is a column vector. Right? So after we take transpose, after taking the transpose, it becomes a column. It is a column-wise form. But now each coordinate, right, is needs to further take a transpose inside. So if you look at the previous V, each coordinate V is a column vector. So taking the transpose, this becomes a row vector. So it is indeed the transpose of this original matrix. Right. By doing so, we don't need to write down all the entry-wise coordinates of this big matrix. Okay, we can just use vectors to represent the columns and rows. And now you see this looks like a column vector times a row vector. So you can do pairwise matrix multiplication. But now, of course, in this case, every coordinate is this one is a column vector and this is a row vector. Okay, so it's a little bit advanced notation in linear algebra, but this is very convenient in many cases. Now, if you follow the multiplication rule of multiplying a column vector by a row vector, you get this pairwise product matrix. Right? And every entry is given by this. Okay, it's a one coordinate of the column vector multiplied by an coordinate of the row vector. Okay. And this is actually the dot product between these two vectors. Okay. So basically, if you look at this big matrix multiplication, the ij's entry following this one, we can see the ij's entry is given by vi transpose vj. Well, vi transpose is coming from the ith row of this column vector. Vj comes from the jth column of this row vector. That's the matrix multiplication rule. This is the ij's entry of this matrix, product matrix. And it is indeed given by such a dot product between vi and vj. Right? This is a dot product between two vectors. So it will give us a number. That number is the ij's entry of this matrix. And we know that for these eigenvectors, they are orthogonal to each other, right? They are orthogonal to each other. So this is 0. They're 0 if I is not equal to j. And if I equals to j, we are looking at vi times itself, dot product with itself. So that will give us the square of the norm. That is 1. Right. So basically, if I is not equal to j, meaning that if the coordinate is not on the diagonal part, then it's 0. Otherwise, it's 1. So this is indeed a standard identity matrix with ones on the diagonal elements. So we showed that V transpose V is identity, which means that V transpose is actually the inverse of V, because we know that only the inverse times the matrix can be identity. So this actually shows that this guy is the inverse of V. And we can also define this matrix, diagonal matrix, which is formed by putting all the eigenvalues on the diagonal elements. Okay. And usually we do it in a descending order. So lambda 1 is the largest eigenvalue, lambda 2 is the second largest, and lambda n is the smallest eigenvalue. And then we can write out the definition of eigenvalues. Okay, this equation in a matrix form like this. Okay. So I will not go into the details, but this is very similar to this structure where C times VI equals to lambda I times VI. Well, VI is a vector, but now here we are stacking all these eigenvectors in a matrix. So this is kind of, we are stacking all these different number of such eigenvalue equations into a matrix form. But with this one, we can conclude that the original matrix, right, the original symmetric positive semi-definite matrix can be rewritten as V times such lambda times V inverse. You can move this V to the right-hand side by multiplying by the inverse on the right-hand side. Okay, so therefore, any positive symmetric PSD matrix can have such an eigen decomposition. Right? Well, this V, matrix V and V transpose is defined by stacking all the eigenvectors in this way. Okay, V is defined in this way, and V transpose is the transpose of V. And in between, we have diagonal matrix lambda, this big lambda matrix. This matrix is a diagonal matrix formed by stacking all the eigenvalues on the diagonal line. Okay, so this is the standard eigen decomposition. And we can see that up to such a orthogonal transformation, this matrix actually equals to such a diagonal matrix. We know diagonal matrix is kind of the simplest matrix that we can have. And this shows that any symmetric and positive semi-definite matrix can be linked to such a diagonal matrix up to this orthogonal transformation. Okay. So this diagonal matrix is kind of you can view it as similar to the Fourier coefficients, like the spectrum of a signal. Yeah. So this diagonal eigenvalues is kind of the spectrum of this matrix, and this V forms the basis. Okay. And again, by matrix multiplication rule, you can verify that this is essentially lambda I, V, I, V, I transpose. Okay. Following the matrix multiplication rule. And this is a very clear way of visualizing the eigen decomposition. This matrix can be decomposed into a bunch of summations, where each term in the summation is the corresponding eigenvalue multiplied by this matrix. This is a matrix. This matrix is formed by the i's eigenvalue multiplied by its transpose. So this is like the spectrum. You can think of this as Fourier transform. But this is a Fourier coefficients. This is a basis signal. So this is a way of understanding matrix in the way of signal processing. Okay. And we have these many properties. Basically, there are two important structures of this eigen decomposition. One is that V is an orthogonal matrix. So sometimes If we want to take the inverse, then it's very convenient. And this big lambda is a diagonal matrix. It's a very simple matrix. Right? So for example, if we want to evaluate the square of this matrix, meaning the matrix multiplied by itself, then by leveraging this orthogonality and the diagonal structure, we can show that you just need to square the middle diagonal matrix. Well, V and V transpose can remains the same. You only need to square this part. And if you want to take the square root of this matrix, you only need to take the square root of the middle part. And if you want to take the inverse, you only need to take the inverse of this diagonal part. So all these matrix computations can be much simplified once we perform this eigen decomposition. Okay. So up to here, we have so what we discussed is that for this autocovariance matrix, for this CX matrix, because it is symmetric and PSD, so we can perform this standard eigen decomposition, and this will have these nice structures. And the other two comments is that, okay, for every autocovariance matrix CX, it is PSD symmetric, therefore we can perform this eigen decomposition. And the other way is also holds. And in a positive semi-definite and a symmetric matrix can be viewed as a certain covariance matrix of some random variable. Right? So you can construct a random variable for which is covariance matrix equals to this PSD matrix. Okay, so this is everything about this autocovariance matrix. About this one. For the cross covariance, it may not, we cannot use eigen decomposition in general, because in general it is not even square. Okay? Because x and y, their dimension may not be equal. X is dimension n, y is dimension m. So this matrix is not square in general. And for this one, we cannot do eigen decomposition. And for the autocorrelation matrix, this one is also a symmetric and a positive semi-definite matrix. We can also have the eigen decomposition for this matrix. So this is everything about lecture 21, where we start to introduce the n-dimensional random vectors. And all the statistics of these random vectors are characterized by vectors and matrices. And for matrices, we can use linear algebra to simplify to help us understand the structure of these statistics in the high dimensional random vectors. Yeah. And next we can, based on that, we can define the Gaussian random vectors, okay, which is a very, very useful and very special case of random vectors. And intuitively, so before we introduced Gaussian random variables, well, the PDF is given by such a is given in such an exponential form. And I think we have this nice property about Gaussian. Basically, Gaussian is preserved under linear transformation. Okay? If we have a bunch of independent Gaussian random variables, then their arbitrary linear combination is also a Gaussian random variable. You can view this as a function of n random variables, a linear function of n random variables. And this big random variable is Gaussian if all these random variables are independent Gaussian. Yeah, sometimes this will be very useful. If we know these are Gaussian independent, then you can automatically conclude that this is Gaussian. So all you have to do is to identify its mean and the variance. Then you have the PDF. So I will skip the proof here. And this is a very useful property. Okay. And then we can define this Gaussian random vector. We call a random vector Gaussian random vector if every linear combination of its coordinates is a Gaussian random variable. Right? So we know that X, the random vector, is a list of random variables. Right? And if every linear combination of these random variables always gives us a Gaussian random variable, then we call this X a Gaussian random vector. And for Gaussian random vectors, we have two statistics. One is the mean vector. So we denote it as mu, which by definition is the coordinate-wise mean of this random vector. And the other statistic is the variance. But now here because we are looking at the random vectors, so we need to consider the autocovariance matrix. Okay, we denote it as K. And by definition, is given by such a expectation of this matrix. So this is the autocovariance matrix. So we write for a Gaussian random vector, we denote it as capital N, which stands for normal distribution. It's capital N, mu, and K. Now this mu is the mean, and K is the autocovariance matrix. Right? This is exactly the same as the single, the one-dimensional Gaussian random variable case, except that these are numbers, scalars in the one-dimensional case. But now in the higher dimension, mu becomes a mean vector. And the autocovariance, the variance becomes this autocovariance matrix. Yeah. And basically, we can show that for this Gaussian random vector, every coordinate is in fact a Gaussian random variable. Okay. So basically, for Gaussian random vectors, everything is Gaussian. Coordinates, every random variable in each coordinate is Gaussian. And every linear combination of these coordinates of these random variables is also Gaussian. Everything is Gaussian. And we have this generalized property, which extends the result from the single one-dimensional case to the higher dimensional case. In one-dimensional case, we know that if we linearly transform a Gaussian, so okay, if X is Gaussian and we look at AX plus B, then this is also Gaussian. Right? This is for the one-dimensional case. But for higher dimensional Gaussian random vectors, we have a similar conclusion. Let X be a Gaussian random vector, and let Y be another random vector defined by a linear transformation of this X. This Y equals to a certain W, matrix W times X. Then Y is also a Gaussian random vector. So Gaussian is also preserved under linear transformation in higher dimensional space. And there's no restriction on this W. It can be any matrix as long as it is compatible with matrix multiplication. So W can be a non-square matrix. Right. So because X may have dimension n, x1 to xn, but Y could be dimension m. In that case, this W is m by m, right? So W can be a non-square matrix. Yeah. And this property D is a very nice property that we will use in many cases. Now, let's consider this Gaussian random vector, right, denoted by mu and k. So the mean and the covariance matrix is given. Now, suppose that this covariance matrix is a diagonal matrix. We know that the covariance matrix is defined, this autocovariance matrix is defined as in this way, right? So in particular, the ij's entry of this autocovariance matrix is given by the covariance between xi and xj. Now, if this is diagonal, then this means that all these random variables, they are uncorrelated for I not equal to j. Right? Pick any two random variables in this random vector. They are uncorrelated if this covariance matrix is diagonal. If K is a diagonal matrix, right? So we can imply that xi, xj uncorrelated for I not equal to j, right? They have to be different. And because this is Gaussian random vector, right? So everything is Gaussian. So xi, xj, they are Gaussian. Now for Gaussian random variables, we know that any two uncorrelated Gaussian random variables is also independent. Right. So in this sense, these coordinates are independent, basically, if this autocovariance matrix is diagonal. That essentially means that all the entries of your Gaussian random vector are independent Gaussian random variables. This is a special case when this is diagonal. So we can see that indeed this autocovariance matrix and the mean are the sufficient statistics for this Gaussian random vector. Once we have these two matrices, once we have this autocovariance matrix, we basically know everything about the pairwise relation between all the coordinates of this random vector. Now the last property is the PDF, joint PDF of this Gaussian random vector. Right? So let's say for a Gaussian random vector, we know its mean vector and its autocovariance matrix. Given these two, we can write the PDF of X in this way, where the PDF of X right? Because now X is a random vector, it's a Gaussian random vector. So it is essentially the joint distribution of all these random variables, right? So capital 1 to capital Xn. And these inside, we have the realizations of these random variables. Okay? Such a joint distribution is given by this exponential form, which kind of looks similar to the one-dimensional case. We can compare it with the one-dimensional case. Right. You see that we do have this exponential here. And inside, in the one-dimensional case, we have x minus mu squared divided by sigma squared. Right. And this can be understood as x minus mu times x minus mu times sigma -2 divided by 2. Right. If I write it in this way, then it looks similar to what we have here. But this, in the high dimensional case, is given by the quadratic matrix vector multiplication form. K inverse, K denotes sigma square here. It's the autocovariance, which means the variance in the one-dimensional case. So K inverse is sigma squared to the inverse. And x minus mu transpose times this inverse covariance matrix times this x minus mu again. So this is matrix vector matrix multiplication. It's a quadratic form. And for the coefficient part is also very similar. We have square root of 2 pi, which means 2 pi to the power of 1/2. Well, this 1 represents that we are in the dimension 1, right? But now we have n-dimensional, so it's here we need to take this to the power of m, right? And here is the square root. We have this square root of sigma square, right? Sigma square denotes corresponds to this autocovariance matrix here. So it's K. This matrix takes the determinant to the power of to the square root. Okay, so this is the determinant of this matrix. But in the one-dimensional case, determinant simply becomes the absolute value. So it doesn't matter because we have square here. So this is the PDF of a general high-dimensional Gaussian random vector. And in the two-dimensional case, this one can reduce to the, I think it's lecture 19 or 18, where we introduced the joint PDF of a pair of Gaussian random variables. This K sort of the cross correlation, that row, parameter row of a pair of random Gaussian random variables. Right. In lecture 19 or 18, we have a PDF for a pair of Gaussian random variables. Yeah, this K generalizes that row. And again, I will skip the proof here. If you are interested, you can take a look. It is basically, I think we leveraged this eigen decomposition of this autocovariance matrix. Yeah, the proof is actually non-trivial. We will do a transformation so that after this linear transformation, this random vector has independent Gaussian coordinates. And because they are independent, we can derive the joint PDF very conveniently. And then we have this PDF, and then we can go back, derive the original PDF, because Y and X are linked
through a linear function. So we can apply the fundamental theorem of random variables, right, to compute the PDF of X from PDF of Y. Yeah, so this proof is actually very interesting. And then for this random vectors, we can also do this so-called minimum mean square error estimation. Right? And the idea is exactly generalizes the one-dimensional case. Right? We have a we have an unknown random vector to estimate. Right? This random vector has a certain underlying PDF. We observe another random variable y, right? That comes from this conditional PDF. Now, given this observation, we want to build an estimation of X estimator on Y. And this is through this minimum mean square error estimation framework. But now, since we have high dimension, since these X are in the high dimension, so we are going to, our mean square error is also generalized to the high dimension. It's basically looking at the error of each coordinate, each i's coordinate. This is square error between your underlying random variable in the i's coordinate and your estimation, the corresponding estimator for the i's random variable. Okay? And then you sum up all these estimation errors over all the dimensions. It's a very straightforward generalization, right? So this is the minimum mean square error estimation in the high dimensional space. And we can also have that orthogonality principle. So in the end, we can have these two estimators. One is the MMSE estimator, and the other is the linear MMSE. So for the MMSE estimator, it takes the same form as before, which is a conditional expectation. But now these two are random vectors, so we need to define this conditional expectation in this high dimensional space. So in particular, precisely it is defined in this way. It's the a concatenation of these coordinate-wise conditional expectations. However, each conditional expectation is conditioned on all the entire random vector y. Right? It's conditioned on y1 up to ym. It is not up to the random variable yi. It is for the entire condition on the entire set of random variables involved in y. And this is when we have no constraint on this estimator class, right? The MMSE estimator. But when we constrain this estimator class to be within the linear class, then we have this linear MMSE estimator. Okay. Now this estimator is given by this form. So we can see that all these are statistics of these random vectors, and the random variable y is only involved in here. So the entire estimator is indeed a linear function of y. Right? So it's a linear function of the random of your observation y. And to construct this estimator, you need to calculate the mean of these random vectors, as well as their auto covariance matrix and the cross covariance matrix. Okay. So this generalizes the one-dimensional case. So everything becomes vectors and matrices. So this is the general MMSE framework for random vectors. But for Gaussian random vectors, this MMSE estimation can be simplified. Basically, I think in the one-dimensional case, we have the same result, right? So in the one-dimensional case, we know that these two estimators, they are equivalent if the underlying random variable is Gaussian. And here we have the same conclusion. If x and y are jointly Gaussian random vectors, then these two estimators, they are the same. So basically, for Gaussian random vectors, it suffices to consider linear estimators only. So that is the key message. And again, I will skip the proof. And this property is again a generalization of this one-dimensional case. In the one-dimensional case, we have this result. If x is Gaussian, if x and y are Gaussian, then this is also Gaussian. This random variable as a function of y. It's also Gaussian. So here is the same thing. So if x and y are jointly Gaussian, then given condition on this realization, the conditional distribution of x is Gaussian. I think I should write it in this way. So basically, this is Gaussian. This is a one-dimensional case. And for this PDF, we have the formula in the one-dimensional case. You can check the previous slides, but it is exactly the same as what we have here. So here we can generalize this property to the higher dimensional case. So the conditional PDF if these are random vectors, this is also a high-dimensional Gaussian distribution, multivariate Gaussian distribution, and the mean. Now, because it is this conditional distribution is Gaussian, so we to characterize the PDF, we just need to know the mean and the autocovariance matrix. So in this case, the mean is given by this conditional mean, which is essentially the linear MMSE estimate of y. Right? So it's given in this way. So condition on this realization, x has a Gaussian conditional distribution, right? And the mean is given by this one. The mean vector is given by this one. The autocovariance matrix, right? The conditional autocovariance matrix is given in this form. Okay, so this finishes the lecture 22. So lecture 21 and 22 are all about high-dimensional random vectors. Right? So I think from all these materials, we can see that generalizing everything in the one-dimensional case to the higher dimensional case is it's very similar. except that we need to use linear algebra, the language of linear algebra, to rewrite all the expressions. Right, so we start with these random vectors. We define this correlation covariance matrices of random vectors, which is basically a pairwise, a collection of the pairwise statistics. And we have to use matrix vector notations to make everything, make the notation simplified. And this is the power of linear algebra. And especially for this autocovariance matrix, because it's symmetric and positive semi-definite, we can have this icon decomposition. And in many cases, this decomposition is very, very useful to help us simplify the calculation and understand the key properties of this correlation, covariances in the high dimensional space. And then in lecture 22, I think we pretty much, so all these properties are generalizations of the one-dimensional case. Okay, so there's nothing new here, except that we're talking about random vectors. So you can directly leverage all these properties to complete your homework. Like these estimators, you just need to figure out how to identify these mean vectors in the covariance matrix. And they have a precise definition in lecture 21, right? It's basically pairwise, computing the pairwise statistics, correlations, covariances, and stack them into a matrix. Okay, so for the last 30 minutes, we have 4 lectures left. So starting from lecture 23 and to lecture 24, we are going to talk about a very important property, is the limiting behavior of random variables, or the convergence of random variables. These concepts are a little bit advanced, but they are actually very fundamental and very important in the probability framework. The motivation is that for random variables, we know it is defined as functions, right? A random variable x is a mapping from outcome to a real number. So it is a function. And for functions in calculus, we know that for functions, we care about these basic properties like continuity or some limiting behaviors, limits basically. So here we are going to do the same thing. We are going to look at the limiting behavior of a sequence of random variables. In calculus, we have a sequence of numbers or a sequence of functions, and we look at their limiting behaviors and the convergence behaviors. Here for random variables, we can do the same thing. So in many cases, we are interested in a random or infinite sequence of random variables. Okay. And this is very important later on when we characterize a random process. Right? if you want to model a random process, model some nature phenomenon using a random process, like a drop of ink is placed into a water, and this dynamic is random, it's totally random, right? You cannot predict that. So, but we can use some random process to model this dynamic, and that will give us a sequence of random variables over time. But time can be infinite or over a very long horizon, right? So that's what, so we always, in those cases, we always need to deal with a sequence of random variables. And we want to understand in the limit, what is the behavior of these random variables? In the end, will they spread, will this drop of ink spread uniformly over the entire water, or they will concentrate at a certain point? So all this, when we talk about random processes, it is always a matter of dealing with the sequence of random variables. So we want to care about this one. So I think I can start with this simple example, which talks about the limiting behavior of a binomial distribution, NP. Right? Recall that a random variable, yn, follows binomial distribution, has the following probability mass function. So yn, let's recall the definition of binomial. It's like you perform n independent experiments. Each trial succeeds with probability p. And yn denotes, the random variable yn denotes the total number of success. Okay. And we have the following distribution. We can calculate that by combinatorics. Right? The probability that we have k success is given by this form. Now the question is, what if n goes to infinity? Right? What if we perform infinitely many experiments, or like we start from 10 and we go to infinity? Intuitively, once we perform more and more experiments, we are expected to see a concentration, because we have if you perform 1,000,000 experiments, you more or less expect that the total number of success will be very close to n times p. Because you have such a large sample size. So the randomness in expectation should be very, very small. And so this is the kind of the behavior that we want to study. It looks like for this kind of regular random variables, in their limits, they will converge to something special. So here we can do the following. We can write as before, as we discussed before, we can write binomial distribution as a sum of Bernoulli random variables, where each xi denotes is a Bernoulli binary indicator of the success of the ith experiment. So every xi is IID Bernoulli. Right, we have done this before. And then we can calculate the mean and the variance of this binomial distribution. And therefore, yn, so we can call this xn a Bernoulli process. Okay? Basically, every experiment is a Bernoulli in random variable, and yn is an accumulation of this Bernoulli process up to a certain time n. And the question that we want to understand is, how does this distribution of yn evolve as n increases? This is the PMF of yn. But if this n goes to infinity, goes to a very large number, can we say something about this binomial distribution? This is a discrete distribution. And this is an illustration of the limiting process. Well, we are looking at the first case where we fix P, we fix the success rate for each experiment. Now, in this numerical example, we fix P to be 20%. And we increase N from 50 to 1,000. And these are the PMFs of this binomial distribution Yn. And we can see that as N increases, in the end, the PMF looks pretty much like Gaussians. And they are more and more continuous because we are performing more and more experiments. Yeah. So you can see that as N increases, the mean will increase because the mean is NP, right? If we increase N, the mean will increase, will also increase. And also the variance will also increase with regard to N. And indeed, we can see that if N is very small, the mean is very small and the variance is also small. But when N goes to a very big number, the mean has shifted to a large value. And apparently, for this distribution, it is wider. So the variance is bigger than the previous small cases, small number of N cases. So we want to see that, okay, in the limit, can we say something about this shape? And indeed, we have a result that characterizes this limiting behavior. Okay. If we fix the success rate and then look at this distribution, then as N goes to infinity, as we perform more and more experiments, we have the following characterization. So if we consider the normalized random variable, right, Yn is a binomial random variable of what have it. Yeah. So if we subtract the mean and divide it by the standard deviation, right? This is a normalization. Consider this normalized random variable. As N goes to infinity, it goes to the normal distribution, the standard normal distribution. Okay. So basically the PMF of this random variable converges to the normal distribution in some sense. And in fact, this can be verified empirically. Like for N equals to 1,000 with 20% success rate, this is the empirical. This is the normalized PMF. I think there are two curves. I think the solid curve is the normalized, is this distribution, the normalized distribution of this one. And the dot curve is the standard normal distribution, right? They match exactly. Yeah. So this is an empirical discovery, but we want to make this formal. And for example, it is not clear what kind of convergence does this. How is this convergence or limiting behavior defined? Like it only says that this random variable is getting closer and closer to a normal random variable. But in what sense? Because we know that normal Gaussian random variable is continuous, but this one is discrete. Right? So we have to be very specific when we talk about these limiting behaviors. And this is just binomial distribution. We will see that for almost all the distributions that we have visited in this course, they all have these limiting behaviors. That's why Gaussian is really the most important distribution in probability theory, because in the end, everything goes to Gaussian. surprisingly, as long as they satisfy some mild conditions. Right? So this is a very interesting behavior that we need to understand analytically, and that's why we need to rigorously define these limiting behaviors for a sequence of random variables. Okay, so I think I will stop here, and if you have questions about the midterm exam, so come and talk to me in the office hours. Okay, see you guys.